Earlier today, we talked about matters of ideal stability and equilibrium. What I want to concentrate on today is the second lecture is on the subject of magnetic reconnection and energy conversions. Magnetic reconnection is precisely the kind of phenomenon that occurs when the plasma is not ideal. And therefore, it's good to begin with a working definition of what magnetic reconnection is. If a plasma is perfectly conducting, and it obeys the ideal Ohm's law, which you've seen me use already, combined with curl E equals minus del B del T, this equation can be written as the induction equation that you've seen a number of times already. Here we write it in this manner. Then there is a theorem which can be stated in two equivalent forms. It's known as Alfvén's theorem. And the two equivalent forms are as follows. It basically amounts to saying that magnetic field lines are frozen in the plasma and no reconnection will occur under these circumstances. And the two equivalent forms are as follows. Imagine you have a plasma which obeys this equation, and you have a circuit C1 which is threaded by magnetic field lines. Imagine that plasma elements lie on this circuit and you have motion for a very short period of time under the self-consistent influence of electromagnetic forces. The circuit would deform itself ever so slightly if the time is small enough. Alfvén's theorem says that the flux passing through C1 would be identical to the flux passing through C2. What C2 is of course obtained from C1 because plasma elements compose the boundaries of C1, and each one of those elements you propagate according to the MHD equations of motion. And therefore they will not be shape preserving, they will change shape. Shape they may not preserve, but the flux they will. Flux threading through C will be an invariant of motion for all times. That's one form in which Alfvén's theorem is stated. An equivalent form is another. That imagine you have a magnetic field line. As Dana Lomka told you, these are real things made up of stuff. So P1 and P2 is stuff, plasma elements lying on that field line. And imagine now the field line actually is moved according to the equations of MHD. The field line will distort, of course, because each element will move differently. However, Alfvén's theorem guarantees that if P1 and P2 lie on this field line, they will do so for all times. Like beads in a wire, they're frozen to the wire in ideal MHD, and there is no respite. Wherever the field line goes, the plasma elements move with it, otherwise known as the non-slippage condition. Plasma elements can slip with respect to the fluid. These two forms of Alfvén's theorem can be shown mathematically to be completely equivalent. I won't go into that. It's worked out in textbooks, for example, in the book by Gurnett and myself. But you have that. And these are very tight constraints on plasma motion. You must preserve the flux through a circuit, and field plasma elements must remain frozen to field lines. What happens if you actually break the ideal MHD Ohm's law? On the right-hand side, you actually have a term R with the property that the curl of R is non-zero. In fact, a more precise condition would be B dot curl of R is non-zero. That would say that the curl of R has no component parallel to the field line. But be that as it may, when you have this condition, you actually break Alfvén's theorem. And field lines can break and reconnect. And in the way in which we have written this, this is like a generalized Ohm's law. It could be resistive MHD, which we'll talk about, where R is merely eta times J, where J is the current density. Or it could be a more general form of Ohm's law with more terms in it, also worked out in textbooks. The common feature being that the curl of this quantity is non-zero. And as I said, R can contain resistivity, Hall current, electron inertia, and pressure. And what are the consequences of this? This is a standard cartoon of magnetic reconnection. Two oppositely pointing field lines come together. They can break and reconnect. First, this was the identity of the field line. After they reconnect, you snip and reconnect. This is what field lines look like. So this then leads to a topological rearrangement of field lines. And why would such a thing occur in nature at all? Is because if you look at systems with different amounts of magnetic energy, and you compare various systems, say various equilibrium systems, you'll come to the conclusion that these systems all do not have the same magnetic energy. Some have less than others. Instabilities are a way of getting rid of free energy in the system, as we talked about earlier. Reconnection is an additional mechanism that allows magnetic field lines embedded in the plasma to relax to states of lower energy. If the plasma were completely ideal, accessibility to lower energy states might be denied the plasma because of Alfvén's theorem. Take, for example, two loops which are connected to each other, pressing hard against each other. As long as the ideal MHD works, there's nothing you can do except have these two loops be interconnected. But if you allow reconnection to occur, you can break and release energy. But this state is not possible unless over a localized region you have non-idealness. Therefore, reconnection can allow relaxation to states of lower energy. The energy can show up as kinetic energy or heating or acceleration of particles, and therefore it's a potent mechanism that is under play in a lot of eruptive phenomena in the universe. I want to make the notion of topological change more precise because the word topology is a bit of a mouthful. But I want to give you an example of the kind of topological change that reconnection allows. This is due to what I would call a tearing instability, where you have field lines that are pointing in opposite directions, and there is a line in between which is often referred to as a neutral line where the magnetic field vanishes. I've drawn this configuration with no field perpendicular to the plane of the paper. Even if that would be there, it would not change materially what I'm about to tell you in terms of reconnection between the field lines that are lying in the plane. If you put in a sinusoidal perturbation to this configuration, you can quickly form these sorts of structures called magnetic islands or cat's eyes or bubbles. These are just plasmoids. These are just words for the same thing. And what you're having here is, due to the imposition of this periodic field line, is that you're breaking up the magnetic field line topology, which was initially consisting entirely of field lines that are going, say, from minus infinity to plus infinity on both sides. But now you have over a region field lines which are closing on themselves. You obviously have lines which are doing the same thing before and after. But you have a new class of field lines which are purely closed on themselves. That topological change cannot be brought about in ideal MHD. You can ask me, what would happen in an ideal MHD plasma if you just impose a sinusoidal perturbation that will tend to do this? You can show, and I won't waste your time doing it, but it takes a few pages of algebra to do, that if you impose that perturbation by force and insist that the ideal MHD equations go to zero, the amplitude of the perturbation is forced to be zero. You cannot impose this perturbation in an ideal MHD plasma. But if you put in a little bit of resistivity, things on the right-hand side of Ohm's law represented by that R, then you can form these islands. In this particular instance, then, the presence of dissipation allows you accessibility to a state of lower energy containing islands, which would not have been possible through ideal motions alone. With me? So this is at the heart of what is going on in reconnection. Now, here is a cartoon from Birch and Drake's Scientific American article showing you that configurations such as this are expected to occur not only in the Earth's magnetotail where MMS mission is directed, where you see structures like this coming out in simulations, and you see plenty of this happening, but also on the solar surface. And you will see more of this discussed in Dana's lecture coming up on solar flares. Eruptive activity like that can lead to coronal mass ejections. For perspective, Earth is this blue dot. This is from SOHO. And it's a spectacular release of material and energy into outer space. And reconnection is a leading candidate for such phenomena to occur. Clearly, the magnetics in a solar atmosphere builds up configurations of very high energy and then releases them suddenly. The challenges for reconnection theory are formidable. We must explain, if reconnection is a viable mechanism, how we build up the energy over a long period of time and then release it suddenly. In other words, the growth of the system, like the substorm growth phase problem that you saw, 35 to 40 minutes of growth, an impulsive increase, and then a sudden loss in energy, right? There are multiple time scales in that problem, some very slow, some very fast, and the burden of reconnection theories is not merely to find one time scale that is fast, but also to explain the whole process of how you store energy and then you release. And these problems are not solved today. We thought we solved them. And I'll explain to you new developments that have actually raised doubts about that. So if you are looking for exciting problems, there are plenty. And certainly most of what I'm going to tell you might give you the impression of things that we understand rather well, but that's not quite true. In the magnetosphere, you just saw this picture earlier when I was talking to you about substorms. Solar wind turns southward, reconnects with field that is northward, we form reconnection layers. Flux is transferred from the day side to the night side. Thinning occurs of the magnetotail, and at mid-tail distances of about 25 to 30 RE, you get your X-line. This everybody agrees on. There is enough data from geotail and satellites that the formation of the X-line at 25 to 30 RE is not a contested matter anymore. What is contested, as I explained to you in my previous lecture, is what is occurring at near-Earth distances, at 10 RE. Is that a reconnection event that releases the energy? Is it a ballooning mode, an ideal MHD instability that releases the energy? Is what we are talking about. But right now, let me focus on the reconnection process itself, where it is not contested, okay? Where we know that we get this sort of things occurring. I'm just doing all this just to set the stage for you to see how in the context of the flare or in context of magnetospheric substorms, two such examples of eruptive phenomena, reconnection is playing a role. Though whether it is responsible for everything that we see remains unsettled. So let's go back to the basics of nonlinear magnetic reconnection model. Most of our compass on reconnection was really set, believe it or not, even after all these years, by this important model of Sweet-Parker, which essentially, it's like Kolmogorov's theory of turbulence. You know, it is very simple, easy to do, checked out by simulations. There hasn't been any theory comparable to this level of rigor yet. I'm ashamed to tell you this, but we do not understand a lot of reconnection things at the level we understood Sweet-Parker, and this was done 50 years ago. So you have field lines pointing in opposite directions, and imagine a steady state situation where the flow is coming in, field lines are merging, and ejected out from the central region as V out. These are the assumptions. This is a two-dimensional system, very idealized, steady state, also idealized. Remember I was telling you we have multiple time scales in every eruptive problem. Sweet-Parker can't be the whole answer to that question because it doesn't have multiple time scales. It's steady state throughout. Incompressibility and classical Spitzer resistivity. So this is your favorite induction equation. On the right-hand side, you have this eta mu 0 del square b, the diffusion term that comes from E plus V cross B equals eta j. Take curl, write curl E as minus del B del T, then curl of eta j, j curl B, you have this equation. Okay? Now, let's do simple conservation laws. That's the beauty of the Sweet-Parker argument. You have Vn coming in, flux, and it's getting chewed up here. So forget about this term. You're just balancing this term against this term. So this is essentially your eta j, B delta. Vb balancing the chewing up of flux in this region. Assume incompressibility, rho times V in times length equals rho times V out times delta, assuming the density is the same in an incompressible plasma. If it is not, then compressibility will give you a little scaling factor of rho in by rho out, but that's a number you can calculate. It doesn't make much difference to the scaling of Sweet-Parker. And then pressure balance means that you have P plus B squared over 2 as constant across this layer, and the pressure comes in, the magnetic pressure is the highest, is the lowest here, the highest farther away because B vanishes here, and what you have is the magnetic energy is being converted, B squared over 2 mu naught to half rho V squared as the plasma is ejected. If you simply look at this, this gives you V out going as V alphane. In other words, reconnection is coming in with the flow, V in, and is coming out with the alphane speed. But if you use these two equations, you come to the conclusion that V in by VA is delta over L. Now delta is this narrow reconnection layer, and L is this macroscopic region. Now that's a small number. How does it scale with resistivity? It scales like 1 over square root of S. Simple playing around with these equations. S is the Lundquist number, usually a very, very large number for solar coronal plasmas for which this was designed. You're looking at timescales of about a year. Parker's model is a completely good model, but totally inapplicable to the problem of solar flares because it actually gives you a reconnection timescale much longer than is actually observed. So Parker's whole point of view was, look, things are going faster than diffusion. I can make things go faster than diffusion because diffusion scales like eta. This scales like eta to the half, which is a lot faster given that eta is a small number. But is it fast enough? No, it is not fast enough. So this then remains a cornerstone of a model in our literature, which is just plain inapplicable, even though it is correct. Doesn't explain this. Yeah? What you're assuming is that you're frozen in magnetic field here in the blue regions and not in this narrow boundary layer where dissipation occurs. So look at this. This is the flux that you would bring in, the frozen influx. But look at what's happening to this flux. It's actually chewed up on the right-hand side by eta j. And that's happening here. Do you get the picture? So everywhere the plasma is ideal. And why is it that diffusion is so effective in a very, very narrow region? Because in this equation, this is a good question you ask me, it allows me to comment. If you look at this equation, it's got the highest spatial derivative, right? If eta is very small, why should that term matter? When will it matter? Can I just throw it out? I'm saying eta is so small, so why not just go there and get rid of this guy and say, I'm great. Try and answer. Derivatives of B are very, very strong. Yeah? You know, this is a very interesting thing. I want to give you a little example very quickly. This is what happens in perturbation theory, right? Suppose if you have a little algebraic equation. Epsilon is a very small number. That's a cubic equation, right? Cubic equation. So it should have 3 roots. Suppose I say epsilon is very small. You say, I'm going to throw this out. How many roots do you have? 2. X equals plus or minus 1. What happened to the third root? You're missing a root. That root has the property that this guy is as large as this guy, even when epsilon is small, because the solution scales like epsilon x cubed going like x squared, which gives you s, x going like 1 over epsilon. You will never get a solution, that solution, unless you balance the so-called small term with the so-called big term. It's not really small. Aha. Let me now go back to the differential equation. J is very, very large there. So even though eta is small, E plus V cross B equals eta J is comparable to every other term in that equation. So where the gradients are strong, eta kicks in, just like epsilon here. So how would you know this sort of a thing? Watch out for the small term multiplying the highest derivative in the equation. Anytime you have that, beware, because the garden path can get you into trouble, because what's really happening is this guy becomes very, very strong. This is the reason why this term, which is coming from here, balances this term here, because this B over delta, this delta guy, is really small. He's like the epsilon guy in that cubic equation. Got it? J is strong. Eta is small, but eta times J is a term of ordered unity. With me, right? Okay. Answer your question? Okay. So everybody realized, certainly Parker did, that reconnection was great, but not enough to solve the flare problem. So why were things so bad with Sweet Parker in terms of reconnection rate? Well, as I said, V in times L equals V out times delta. V in is delta over L, VA. And look at this number. Delta over L is 1 over s to the half. The corona, that number is to about 12 and above. So that's like 1 part in a million. No wonder you're getting reconnection rates measured by V in, how rapidly field lines come together, which is a fractional part of the alpha speed. So Petschek came around and said, there's a geometrical problem with Sweet Parker. The trouble is the delta and L are too disparate. I'm going to cook up a nice model where delta and L will be comparable. Then we can get reconnection rates that are nearly alphanic. Great. He cooked up a model. Along the lines, he was a hydrodynamic shock theorist. And he cooked up a very appealing model in which he said the reconnection rate goes like tau A times log of S. Well, log of S is a hell of a lot better than S to the half. There's a much more weaker dependence on log. And what does it turn out to be for the solar corona? About 100 seconds, much closer to observations. The reconnection problem was deemed to be solved. To this day, a lot of people continue to use the Petschek model in heliophysics in all kinds of circumstances, even though it relies heavily on an assumption that is not correct, which is that the one that became evident when people actually went into numerical simulations. When they went into numerical simulations, what they found was computers helped. You know, this is where I was telling you to be careful about simulations. Simulations can teach you things that analysts can screw up about. And this is an example of that. Well, it started really 1979, 84, but the paper which really shook the field was the paper of Biskamp in 1986, when what he did was that he actually set up configurations which were uniform resistivity in the plasma, high Lundquist number, S, and he tried to get the Petschek mechanism to go. He found that you cannot get Petschek to go unless you put in a lot of localized resistivity near the X point. In other words, he had eta to be small. But if you went and the code is running, you go and locally enhance the resistivity to a very high value by hand. Don't ask me why. People gave hand-wavy arguments. You will get Petschek. Okay, let me show you an example of this. And it's done in my group a long time ago, but certainly we were not the first. Very far from it. There were many, many people who did this thing before us, just as well. But I show this to you because it's something that I do have in my possession. Suppose you set up a vacuum field in a solar corona. This is obeys curl B equal to 0. Remember, Dana was talking to you about force-free models and vacuum models. So this is a vacuum field. And imagine you're twisting photospheric foot point motion. Look at the initial configuration. It's got an X point, right? This is a high Lundquist number plasma. So if Petschek is realizable, this has a damn good chance of being Petschek-like as you start switching, because you already built that X point that Petschek loves in the initial state. Well, within about 30 alphane times, see what you're getting. What does that remind you of? The Sweet-Parker layer. Even though you started out with a geometry that was clearly favorable for Petschek, you are producing configurations which are Sweet-Parker-like. You can get it to be Petschek if you go by hand in the code and change eta while the code is running to a very high value. What would be the argument for that? People usually say, well, the current density is getting too strong, so you have kinetic instabilities that are not determined by the MHD model. You have to do kinetic theory, and that will lead to the enhancement of resistivity. Whether that is so or not is a difficult question. I can tell you that when these calculations have been done carefully, it is sometimes found that the instabilities produce additional dissipation, but not where you need it. So it isn't that this is a foolproof thing of any sort, but if you insist, as I do, that I won't fool around with parameters, resistivity is small, and I'm going to try to understand what's going on with the dynamics, it doesn't matter where you start, you end up with Sweet-Parker. So there is no Petschek. What was the screw-up? The screw-up was that Petschek never really did an asymptotic calculation, and it's very hard to do. That's why he didn't do it. He was a smart guy. But you will see how elements of his construction will come back to us and help us in a different context. But what really happens in this problem is that it is very hard to do a matching between an ideal layer and a resistive layer in a nonlinear boundary value problem, which will tell you how the layer actually deforms. And it has been done in some special configurations by Russell Culsred, who actually demonstrated that the Petschek model is manifestly wrong, and we have moved on from there. People still continue to use Petschek. Old traditions die hard. I don't know what else to say about that. But I don't think it's justified in any case when the resistivity is low. Now, all of these models, Sweet-Parker and Petschek, were steady-state models. But I was telling you that most problems do with eruptive dynamics have two timescales in them, a slow growth phase and then a sudden interruption. So therefore, the reconnection dynamics must at the very least account for two of these timescales. So this is what I'm saying. The magnetic configuration evolves slowly for a long period of time, only to undergo sudden dynamical change over a much shorter period of time. And in many of these cases, you get singular current sheets, current density extremely large, and this is a classic multi-scale problem coupling large scales to small. Dana will talk to you about solar and stellar flares, and I'm sure he's going to mention to you impulsive flares, impulsive acceleration, and things like that, so I will not spend any time on that. What I'll do instead is talk to you about magnetospheric substorms, which you fortunately got introduced to already, and I won't dwell on that. In particular, I'm actually worrying about the problem of substorm onset. And this picture that I've gone through already, so let me not dwell on it again. So what I'm after, I'm going to just pass on this because I explained this auroral brightening, and what I'm really trying to get at here is that if you look at the timescale of evolution, the substorm onset starts out with local brightening. But look at the sudden spreading. Substorms too, like flares, have a storage phase where they store energy and then boom, it goes, right? Somehow the whole reconnection problem must be slow at fast and then very rapid. A really, really important problem that no steady-state models by definition can address. So you have to do the time evolution problem. This is what I was trying to tell you about these Otani timescales, right? Slow phase, 30 to 45 minutes, a growth phase of the current density, and a disruption, the 2-minute problem. Enough said. People came to the conclusion, and we will revisit this conclusion, that you cannot find this solution within the realm of the resistive MHD model. Because what we had with Sweet-Parker, we had Petschek. Petschek was wrong. Sweet-Parker was right. Sweet-Parker gave you one time scale, much too slow. So what do? You start looking for solutions that lie outside of the realm of resistive MHD, and it didn't take a long time for people to figure out that all these terms which are in the textbook, so if I move this to the left-hand side, it's E plus VI cross B. VI is the ion velocity. That's almost like the fluid velocity, right? Because the center of mass velocity in the presence of ions and electrons is MI VI plus ME VE divided by MI plus ME, right? But ME is so small compared with MI that V is almost equal to VI. So you're back to your ideal MHD Ohm's law on the left-hand side. E plus VI cross B equal to 0 or E plus V cross B equals 0. Take your pick. First thing that breaks it is eta J. That was what Sweet-Parker reconnection was about. But you know where that story led. Well, what did we leave out? We have other terms: electron inertia, pressure tensor, Hall current. Well, how important are these terms? Well, if you're looking at resistive MHD systems which are very collisional, then of course those terms are not terribly important. But you can do a scaling argument to figure out how important the other terms are. So let's do this game. Move this guy to the left-hand side. He's VB. And scale him for every other term in this equation, just to check how large these terms are. Okay? So the first term is VB divided by this. That gives you LV over mu 0 eta E Rm, where L is the characteristic length of the reconnection layer, not the system size. When Dana and I introduced the Lundquist number, we had capital L instead of little l. The only difference between L and little l is the system size, called S, and little l is the magnetic Reynolds number, defined with the length of the current sheet. Okay? So don't be confused by S and Rm. You could say S is a special case of Rm, with L being equal to the system size. Okay. So that's Rm, and Rm is typically a rather large number, so this term is typically much larger than this, unless J is very, very large, as we discussed. Then you compare other terms, like 1 over 2. That scales like L over C over omega PE. This is the electron skin depth. This is the current sheet width. 1 over 4, that's the Hall current term, is V over VA, L over C over omega PE. 1 on 3 is the pressure tensor term. This is how it scales. It's good to have the scalings in front of you, because you cannot make uniformly valid statements about every plasma that you're in. It all depends on how the numbers come in. But what you can see is that if the length of the current sheet becomes of the order of the ion skin depth, certainly Hall currents are very, very important to keep in mind. The similar true is pressure tensor. So this gave rise to a whole new branch of work, which is called Hall MHD, and this actually focused on studying the role of the Hall current and the pressure gradient in an Ohm's law, okay, where you not only have resistivity, here 1 over S is the Lundquist number, dE square is the electron skin depth. This is written in dimensionless form, and this is the ion skin depth. Beta is electron pressure. What we are now doing is to look at highly collisionless systems in which eta is not the dominant dissipation mechanism. Other collisionless mechanisms, because eta depends on electron-ion collisions dominantly. These other terms, though, they don't rely on collisions. So in collisionless systems like the Earth's magnetosphere or tail, where the density is extremely low, where collisions are nearly negligible, you can just about forget about this term, right? And it's going to be dominantly driven by these terms. So let's look at situations where we first look at the consequences of resistive MHD and then turn on these terms and see what they do. For that, are you guys with me? I'm now doing what you would call Hall reconnection, in which Hall current and pressure gradient are coexisting with the resistivity terms. Okay, what you will see, and let me go directly to a comparison, and then I'll return to this. Imagine we're doing a simulation. The field lines pointing in opposite directions, and we give it a gentle push. All right? Either you give it a gentle push or the system is unstable in its own right, whichever. The nonlinear evolution is what you want to focus on. You can put in a field, what is often called a guide field, perpendicular to the plane of the paper. And here we call it BT. And you impose this. Now let's compare the results of resistive MHD with Hall MHD. Resistive MHD holds no surprises. What does this remind you of? Which model? Parker. What reconnection rates would you get? You know the answer. Scales like 1 over s to the half, rather slow. You get current sheets which are almost of the system size, electric field pointing out on the plane of the paper, the same level of localization, and narrow jets coming out. Okay? Now with the same initial condition, you turn on the Hall terms. After an initial period where the system looks like resistive MHD, it spontaneously readjusts itself to form this configuration. I didn't go and fool around with the resistivity or do anything of the sort. All that we did was that we were running the original simulation with purely resistive MHD and we ended up on the purgatory of Sweet-Parker. Now we say, aha, no, I don't want to do that, I've been there enough. I'm going to keep the Hall currents on and see what happens. Transiently, you see Sweet-Parker, and then see what happens. You get a decoupling between the scales of the current density out of the plane of the paper. Electric field is on a scale of ion skin depth. The current density is still narrow and thin, but much more X-point-like. The jets are much more X-point-like. What does this remind you of? The Petschek model. Except Petschek was doing this with only resistivity and claimed you can get there with resistivity alone. What are we finding rather remarkably? That if you keep the Hall currents in the problem, the system spontaneously adjusts itself to form a Petschek-like geometry. So, will the configuration support fast reconnection? Well, you go ahead and do that. Measure JZ. This is the picture with resistive MHD. This is with Hall. This is the rate at which you're chewing a flux. D log psi dt is 1 over psi d psi dt. This is a log plot. See what's happening? Resistive MHD remains in this curve. This one shows an explosive growth phase. In short, then, you are getting into the intervention of Hall MHD effects, a slow phase transiently that then explodes and becomes really fast. So Hall MHD then within itself would appear to have all the ingredients you need to understand impulsive phenomena. Well, when will Hall effects play a role? This is what was predicted by Ma and myself in the space community, but even before us in the fusion community, this problem was of interest. So we have a criterion. Start out with a current sheet which is not so thin, and you're driving reconnection, the sheet slowly thins down. Great. At a certain point, delta Sweet-Parker, which is a thin current sheet, is going to fall below the ion skin depth. As soon as it falls below the ion skin depth, the Hall effects will kick in. So the growth time is as long as for the system takes to produce a thin current sheet from a larger, wider current sheet, which is below the ion skin depth. Once you do that, the system takes off on its own and gives you a fast reconnection phase. This seems too good to be true, but true indeed. This was seen in fluid simulations. Guess what? People did fully particle and kinetic simulations. The same feature. This is one of simulations of Drake, Kassak, Shea. They're not doing Hall MHD necessarily, they're doing PIC, but the same qualitative features hold up. Hall current matters, pressure gradient terms matter, and you're getting fast reconnection out of a slower transient phase. Okay? Great. It seems like, what about experiments? This was the MRX experiment at Princeton. Masaki Yamada got the Excellence Prize because he did this experiment. This is what happens in a highly resistive plasma. You get this X-point form, and look at the labels. These are the levels of fields that you get from the reconnection geometry. He is looking at, trying to figure out what the label is. J. That's the current density that he's looking at. Look at what happens when he reduces the density of the system, so the system becomes much more collision-less. This is a separate experiment. You get much more X-point-like configurations. So clearly, in the weakly collisional regime, as you get into a case which is of greater interest in solar or magnetospheric plasmas, the mean free path is actually larger than the system size. Hall current and pressure gradients play a much more important role, giving you access to a new regime of fast reconnection. How fast is the reconnection? It's of the order of 0.1 VA. How sensitively does it depend on dissipation? Negligibly. It doesn't have the S to the half dependencies. It has that as long as it stays in the Sweet-Parker regime. When it transitions, the reconnection rate jumps up. We're doing great. We really thought we solved the fast reconnection problem. So when you get to be an older person, you start counting how many years in research you have left. Right? So I often do that. And I thought to myself back in 1996 that at least help solve one important problem. The impulsive onset problem of reconnection is solved. It was seen in simulation, it was seen in experiments, little did I know. I had a discovery later which proved me wrong, but we'll get to that later, okay? Just to let you know, there is never a respite. I mean, for those of us who grew up with reconnection and turbulence as twin problems in plasma physics we want to solve, you had no prayer of solving turbulence problem in my lifetime. Come on, no. K minus 5/3, it sits there. 200 years it sits there. Nobody has solved it. To say that you will solve that problem before you retire is a lot of hubris. But the impulsive onset problem in reconnection just seemed a lot easier. Everything points the right direction. So you could see why I could congratulate myself a little too early and say, hey, did one thing right, right? But no, you'll find out that we are all stuck anyway. Well, here there's just a linkage telling you that this ratio that I'm talking about, di over delta Sweet-Parker, this is a very simple thing. Calculate delta Sweet-Parker from Sweet-Parker model. You know the resistivity. When the ion skin depth exceeds delta Sweet-Parker, you'll have an impulsive transition. Tabulate all. Look, looks very good in all cases except the interstellar medium, where di over delta Sp is smaller than 1, which can never, where Hall currents are never important. It's always condemned to be in the state of Sweet-Parker reconnection. But every other system, it would seem like will be amenable to Hall reconnection. Well, how about this favorite magneto-tail problem that we are working on? How well do we do? Well, you start out with the dipole field that Dana introduced you to, the plasma and everything in it. You drive it with a solar wind. Remember I was telling you current sheet thins down? Well, truly it does, and you form this X point, just like in the observation, and the X point propagates inward. This is Otani's picture that we were trying to reproduce. How well do our simulations do? We get the growth phase right, we get the impulsive onset right, calculating this at 12 Earth radii, and then this thing falls. Well, does this fall as rapidly as seen in the observations? No. It actually falls much more slowly. This was the reason why we felt the reconnection by itself was not enough to explain the substorm growth. Because if you looked at the Otani plot, this guy is a few seconds. What is it in our simulation? Like 20 minutes. What do we do well in the simulation? We do fine in the growth phase and the impulsive onset. This is like 45 minutes in our simulation, exactly like it is in the observation. We also get this enhancement, but we don't get it right, which is why our mind turned to ballooning instabilities. At near-Earth distances being a possible mechanism for substorm onset because it could proceed much faster on alphanic timescales, much faster than we found in our simulations. I'm not going to revisit that controversy again, but now you at least understand the problem. If you simulate the magnetotail in 2 dimensions with Hall MHT, you get a lot of things right, but you don't get this guy right. Unless you go back and put up the resistivity or something, very high unrealistic values at the X point to drive your reconnection faster. A lot of global codes do that. They run their codes necessarily with such high values of resistivity that they end up getting, they do it for numerical reasons, very fast disruption timescales. But that's not the parameter of the magnetotail. The magnetic tail is a highly collisionless system. Eta is very, very small. All the help you've got is from the Hall current, pressure gradient, and all of that. And if you do the game right, you don't get it. You don't get the right time scale. This is my point of view. I love reconnection, and I wish I could say that the substorm onset time scale makes sense in the context of reconnection. I don't see it as yet, which is why I turned to ballooning, which is also not enough. So that problem remains unsolved. Ballooning takes you part of the way. Well, all of this stuff is now the stuff of MMS, launched 2015, a very exciting mission. It's probing the electron diffusion region, where the current density is very intense. We'll have lots of stuff to learn from this mission as we go forward. But what screwed me up in terms of claiming that the impulsive onset problem was solved? Well, I told you that Sweet-Parker was dead, right? Can't find anything in the Sweet-Parker model. And then our simulations got more sophisticated. This is the Sweet-Parker model. Remember, just to remind you once again, extended thin current sheet produces characteristic timescales s to the half, which is much too long. Well, a graduate student wrote a great thesis. Nuno Loureiro, now an assistant professor at MIT, made an interesting point. He said that if you look at the thin Sweet-Parker current sheet and examine it for its stability, you will find it's actually unstable to a very fast resistive instability, which has not been talked about in the literature. And when I first saw his work, I realized my first impulse was to disbelieve it, because the theory for resistive instabilities was done by extremely good people. Marshall Rosenbluth, Harold Furth, John Killeen. They were absolutely leaders in the plasma physics business. I can tell you Rosenbluth was my postdoctoral advisor, and he was absolutely brilliant with mathematics. And I worked through his entire paper on resistive stability, and there was no reason I had to question any conclusion in that paper. Here comes Loureiro and tells me that Rosenbluth missed a major instability. Why would he miss the major instability? So my first disbelief was because I couldn't see how the growth rate would come out of Rosenbluth's dispersion relations, but I did some work and I realized the solution was actually extremely simple. Rosenbluth dealt with the stability of a thick current sheet of width A with no dependence on the Lundquist number. But the Sweet-Parker layer is a very narrow layer. Its width scales like 1 over s to the half. What would Rosenbluth's calculations predict if we started with a sheet which was a very thin current sheet with the width dependent on the Lundquist number? Proved to myself, and it published a paper on this, that it actually can be derived from the Rosenbluth dispersion relation. So everything was fine. Rosenbluth's dispersion relation was fine. He just did not consider the issue because, the Sweet-Parker layer comes about in the nonlinear regime. That's where you not usually start. You usually start with smooth current distributions and you wait for the system to get down to the Sweet-Parker layer. That's a highly nonlinear problem, and Rosenbluth was not interested in that problem. He was just merely looking at tearing instability of a fairly large plasma sheet. So the Loureiro instability was great, very fast instability, but it was a linear instability. Does it do anything interesting nonlinearly? That was the critical question. Well, this is what it does nonlinearly. Watch this movie, okay? Here is a thick current sheet thinning down. And it is thinning down, and it will form transiently a Sweet-Parker layer. But then, when the Lundquist number exceeds a certain critical Lundquist number, 10,000 it turns out, starts out becoming linearly unstable to Loureiro, but it does more than that. Forms these plasmoids, tons of them, very impulsive. Okay? And these magnetic islands or bubbles or plasmoids, as I call them, they coalesce, they're ejected, and it's a near chaotic phenomenon. You could not predict which way the plasmoid was going to go once it is formed. It's a nonlinear dynamical system, very sensitive to initial conditions or noise in the system. But it doesn't matter. The qualitative behavior is always this thing, big plasmoids forming, gobbling up the small plasmoids through coalescence and stability, and the whole damn thing continues as the system runs out of flux. Well, this is resistive MHD. It has got no Hall current, it's got no pressure gradient, and it is virulently nonlinearly unstable. The Lorero instability was just a beginning point. And so there's a little history here. If you go back to the literature, you will find that prior to Lorero's work, there were a whole lot of people who worried about Sweet-Parker current sheets becoming unstable to plasmoids. If you look at Biskamp's book, he says it'll enhance the reconnection rate, but doesn't make a big deal about it. He saw that in his simulations, just didn't quantify it. Lorero carried out a good linear analysis. I did the nonlinear theory. And what I found, in fact, is that if you did the scaling study carefully, in the nonlinear regime, and by the way, this is not now confined anymore to resistive MHD systems. So I cite all these people. Lapenta wrote a very nice paper in PRL 2008, Kassak, Samtani, Dalton. It's a long list of people now who have actually found that a thin current sheet is unstable, independent of whether you are in the resistive MHD system or not. But let's keep our attention to resistive MHD. How does the reconnection rate scale? You want to figure out how rapidly you are connecting flux? Well, up to a Lundquist number of about 10,000, you're following the Sweet-Parker law. Reconnection time is increasing. This is what made Sweet-Parker uninteresting, right? High Lundquist number, reconnection time takes too long. Over 10,000, this thing turns over and becomes independent of S. Well, how rapidly is the reconnection rate? 0.01 VA. Not quite as rapid as 0.1 VA, which Hall gives you. It gives you 0.01 VA, and what is more important, it's liberated from this very burdensome scaling law. That means if the Lundquist number exceeds the 10,000, the system will nonlinearly evolve through the excitation of the nonlinear plasmoid instability into a regime where the reconnection is completely independent of the Lundquist number. What more does a man want? We got there, right? So you can now get fast reconnection without even going outside of the Sweet-Parker model. Just go to Lundquist numbers high enough. Now you will say, that's not high enough, you need to go to 0.1. Well, then Hall will help you. It'll get you the remaining distance. But the claim that you cannot get fast reconnection in Sweet-Parker was wrong. What was wrong with Parker's model, this canon of the literature? As you know, Parker is God in our field. 50 years his model stood. But Parker had assumed that the Sweet-Parker current sheet of system size length was stable. Everything in his argument relied on the stability of that sheet, conservation laws and everything. But the sheet is itself unstable. After a short period of time, it breaks up. Now, why is this a monkey's wrench in the impulsive onset problem? Think about it. What was my criterion? My criterion was take that thick current sheet, form the Sweet-Parker current layer, wait until the width of that current sheet falls below the ion skin depth, then you're off reconnection. But what if the Sweet-Parker layer is unstable? Well, you form this Sweet-Parker layer, you don't have time to build up energy. It's already breaking up into plasmoids before you get to that transition criterion. Because the moment you form that Sweet-Parker current sheet, the plasmoid instability kicks in. It's no longer going to wait for me or anybody else till that width falls below the ion skin depth. It's going to go unstable. So where is the storage phase? We had victory, and we discovered the plasmoid instability, but the plasmoid instability kills. Such is the way of nature. Ultimately, she will hold forth, and we mortals think we understand something, and then something else will come and get in the way. I have a scaling argument here that tells you why this thing works, okay? Let me not go over that right now, because you can study this. We can demonstrate by simple scaling arguments that the reconnection rate becomes independent of S. This is what I mean by saying that you must always do some theory to make sure that the results from your simulation. You know, I think what happened to people is that they ran their codes and saw the plasmoid instability and thought it was a numerical instability. What I give Lorero a lot of credit for, he actually did the mathematics for the linear instability correctly, so that you actually got a growth rate, so you know that if you saw the instability in the system, this was not because you were running out of resolution. So we could benchmark. the linear growth rate, and then go to the nonlinear regime with confidence to find the result that really matters, but the reconnection rate becomes independent of S. And this is what really happened. And you have to make sense of this using the scaling law. So let me continue a little more. I'll give you a break at 1 hour. So what happens now? Well, we made up a new phase diagram of magnetic reconnection. And this is now being a stimulus for a lot of experiments that are being done at Princeton. There's a new MRX experiment called FLARE that Masaki Yamada and Bhattacharjee are building. There's also an experiment in Madison, Wisconsin called TREX. Of course, nature, the solar corona and the magnetotail, already in the realm of high S, is a great laboratory for studying these processes. And have we seen plasmoids there? Yes, we will. I will demonstrate to you. So in the beginning, life was made up of Sweet-Parker reconnection and Hall reconnection. And that was fine below a Lundquist number of the order of 10,000. Once we went beyond 10,000, now we have plasmoids. So the possibilities become plasmoid-dominated reconnection, a whole new realm of things. And you want to ask yourself, what happens if you put Hall effects in that? The essential thing is that at 0.01 VA, I'm going to show you 3 runs. These are traces. This is a Sweet-Parker rate. And these are the rates that you get, runs that you get at different values of the Lundquist number and Hall currents as you include plasmoid as well as Hall in your model. These are predictions of theory. There are two ways in which you can get fast reconnection in the presence of plasmoids. If you turn on the Hall current, one of them just gives you a pure X point with the Hall effects pushing the plasmoids out. And that gives you fast reconnection. But there is another possibility, which is a possibility that is seen in particle and cell simulations, where you get an X point, but the current sheet extends and continues producing plasmoids. And we thought to ourselves, can we get this out of Hall MHD? It turns out that you can. We did the largest Hall simulation that is done by anybody so far. These are very, very long systems. And see what happens. First you get Sweet-Parker layer. That becomes plasmoid unstable. Hall effects continue, gives you the X point. But the X point itself becomes unstable, produces plasmoids over again, and the process repeats itself over and over again until it has run out of flux. If you look at the reconnection rates that you get out of these systems, these are like 0.1 VA. So plasmoid reconnection helped by Hall takes us to 0.1 with one very major difference. Without Hall, in the presence of plasmoids, you're already in an interesting regime. The reconnection rate does not depend anymore on the dissipation mechanism. And this was a fundamental discovery. That you could stay within the realm of resistive MHD and not be condemned to the purgatory of Sweet-Parker reconnection. Therefore, textbooks written on magnetic reconnection from here on can never quite now rest with the Sweet-Parker model as being the only correct nonlinear model of reconnection, even though too slow. Because over a Lundquist number, Sweet-Parker is unstable. Sweet-Parker has stayed in the field for 50 years till plasmoid instability changed it. I think this is a really important turning point in reconnection theory. Well, what about observations? Well before the discovery, Li Zhen Chen, she was my postdoctoral fellow at the time, well before Themis, she was looking at clustered data. And she was measuring islands in the Earth's magnetotail. And Li Zhen used a number of clever diagnostics. So here is her cartoon of what multiple plasmoids would look like. She had no mechanisms as to how this would form. That came later. But she was already, in fact, telling us that you have a lot of plasmoids in the magnetotail under substorm conditions. You get multiple X points. Here is cluster. And if you cross in this dotted line, the BZ would go through a bipolar structure. This is just one of the criteria she actually used. She looked at distribution functions, but she discovered something rather interesting. She found, in fact, that she gets enormous electron flux at all energy ranges, and she was tracking, she's looking at BZ, and this bipolar feature I was telling you about, there are a number of them, and she counts them. And by that token comes to the conclusion on how many islands she's getting in how many minutes, because she knows the spacecraft speed. Her conclusion was that she got 10 islands in minutes. And what was interesting was that when she looks at energization of particles, you would think that the action of the reconnection is really at the X points, and that's where the major electric field is, and that's where the major energization happens. And she surely saw most particles near the X point with the highest energies. Okay? Clearly, the X points produce the largest acceleration. But the number of particles were much higher at the O points. And this was not expected. It was not expected that largest number of islands, largest number of particles would be accelerated not at the X point, but at the O point. Observations like this stimulated Jim Drake to suggest that if you take a volume and you have a lot of islands in it, then you may be able to produce by reconnection a lot of acceleration. This is another story that I won't quite get into, but as far as the solar corona is concerned, look at these blobs. If these are proxies for plasmoid, in the post-CME current sheet, you have this extended heliospheric current sheet, and you have these blobs, which are thought of as plasmoids. And people in MSU, like David McKenzie and others, have made a whole set of papers, nice papers, counting plasmoids in the heliospheric current sheet. So the notion that an extended current sheet produces plasmoids has been known in the observational literature for a while. It's the theorists who are to come up with a convincing scenario of when this might occur. This is a good point to take a break. And let's get together in 5 minutes. Thank you. Yeah, very close. What's the resolution is the question. You know, there's a very nice treatment you can do to say, suppose you do two-dimensional study. How would you plot a distribution function of the sizes of plasmoids against how many that you watch them? That's what I was trying to figure out. And we have a prediction on that. I wasn't going to dwell on this. I'd be happy to talk to you about it. Yeah, let's do it. Yeah. I can work out the masses of things. I thought were important at the time, but I hadn't gone back to the theory to figure out relevance to the numbers. I think if fundamental characteristics. This is great. I mean, I've thought about this a little. One of the things was that in order to map out a distribution function, you need enough of a spatial range in the sizes of plasmoids. And basically, Ligia Gu, who was my PhD student, she tried to do this, and what we found was very interestingly a power law followed by an exponential. But the sizes that we had were not enough to discern much of the power law. Larger range to really vindicate. This might be able to help you with that. These are what observations? These are. Oh, this was, I did this was, sorry, this was the quarter. Yeah. So this is something, if you feel like you have the range, I'll be really happy to share with you. This is really... Yeah. So, well, I'd love to see that figure. Sure. See what kind of scale we're in. Absolutely. In fact, the only reason I took it out is because I wanted to explore more details. I want to do more things on it. Yeah. Okay. Thank you. This sounds good. Okay, shall we start? Thank you. So I was showing you this post-GMA current sheets, and it's very hard to say unambiguously that these are, in fact, plasmoids, because we have no direct measurements of magnetic fields in the corona. We measure with magnetometers what's going on in the Earth's magnetosphere, field reversals, all these signatures. We don't have that. All we have is distant images. How do we know that these blobs are really anything to do with plasmoids? Therefore, the evidence can't be oversold. However, if you assume that there are plasmoids and things like that, then what you can do is to count them, to fit them to distribution functions, like what is the distribution of plasmoids as a function of their size or amount of flux they contain, and the theory makes predictions. Can't get into all of that here today, much as I would love to, because it's a very well-developed theory with very clear predictions. And one of the difficulties that I was just talking to Neil Savani about is that in order to calculate the statistics of plasmoids, theory makes predictions, but coronal instruments have limitations on how large a plasmoid they can actually resolve. One of the nice things is these plasmoids are a lot larger than thin current sheets are. There is a much greater prayer of discerning reconnection in solar context by studying plasmoids which have larger size, even when we can't resolve the current sheet. So there's a lot of work to be done in that area, okay? But let me move on, and you could say, look, you've done all this 2D theory. Nature is 3D. How do you know whether any of this works? Well, what happens in 3D if you go? So we've done 3D simulations now. And what you have is the two-dimensional configuration, as it will not surprise you, ends up being flux tubes extended along 3D. So this Jackson-Pollock-like picture tells you what happens when you have three-dimensional structures growing. They grow like flux tubes, okay? And as the plasmoid grows in size, the flux tube starts overlapping. You get into more and more turbulent setups. And look at this. It's chaotic in third dimension. Now, if you project it, I don't know whether you can see this. You can still see blob-like structures with some preservation of the sense of these plasmoids. Though how to do a theory for these remains an open question. We have simulation results. If you actually go ahead and compute things like reconnected flux or reconnection rate, you can do the following. A three-dimensional system with x, y, and z dependencies has no ignorable coordinate. If it has no ignorable coordinate, then it's very hard to define a flux function on which field lines will lie. It's just like a problem in Hamiltonian mechanics, right? You know the Kepler's problem is solvable because there's access symmetry, has angular momentum conservation in addition to energy, that gives you a nice tight orbit. But if you destroy three-dimensional symmetry, you destroy flux function. So what do you do in a three-dimensional mess like that? Well, what you can do is to define a mean field where we average out the z direction. And that, by definition, does not have any z dependence. You can define a flux function, and you can calculate what the reconnection rate is. We've done this. 2D Sweet-Parker, 2D plasmoid, and 3D plasmoid. 2D plasmoids are a hell of a lot more bursty than 3D are, but the average reconnection rate is about the same. So it's interesting that you get more turbulence, but the average rate at which you chew up flux in the mean field is about the same. So by itself going to 3D, even though it dramatically changes your morphology, doesn't necessarily change your reconnection rate all that much. But reconnection rate is not the only thing. If you plot out the spectra of these systems, they're turbulent systems. So what you're really getting out of this is that if you allow plasmoid instabilities to evolve in 3 dimensions, they will lead to MHD turbulence. And you have a mechanism. You can start out with a perfectly laminar situation. You can form thin current sheets. They'll be driven plasmoid unstable in 2D. In 3D, the instability persists with even greater growth rates, produces chaotic field lines and turbulence. And this is all quantified in our papers, and I won't take a lot of your time. Energy spectra, velocity spectra, you get power laws, and all of this. That's a different story, and what I want to do is to turn to the problem of energy conversion. Lots of issues, but I do want to touch upon the important issue of energy conversions, which was driving this discussion to a point, and magnetic reconnection being a driver of that. We talked about how you get topologies which have lower energy, so you liberated the magnetic energy. Now it turns out that it's very hard to get precise data on energy conversions. We have evidence, of course, in a solar flare that you can have reconnection and enormous energization. As far as that is concerned, those are measurable things. But suppose if you have a reconnection layer and you really want to quantify how much energy is coming in, how much is going out, what exact is dissipation, you need very careful in situ measurements. Of course, we can do simulations galore, and those have been done, and they've given answers. What I want to present to you are some laboratory experiments, like MRX experiments, where this energy conservation issue has been dealt with in some depth, where you have two cores and you have this Sweet-Parker type of layer forming transiently. They do helium, and they are in a collisionless regime. The lambda mean free path of the system is much larger than the ion skin depth, which is much larger than the current sheet width. This is experimentally realizable, believe it or not, in the laboratory. This is resembling what goes on in space conditions, though the scale separation is much larger in space than are in laboratory experiments. So laboratory experiments you have to learn from, but you cannot apply blindly to space cases because the parameter regimes are vastly different. Well, what have we learned from this exercise? Well, there is electron dynamics and electron heating in MRX. They quantify this, okay? In space, if you have MMS, a cluster, guess how you calculate current density? You calculate the difference in magnetic fields and divide it by the density. It's called the curlometer. That's not a very good way to approximate current density unless the 2 points are very close to each other, right? We all know calculus. You can get derivatives in the limit in which delta x is very small, but unfortunately in satellites, delta x is huge. And current densities therefore are damned hard things to measure. In space, the way people do that is through curlometers on the one hand, but also through a measurement of the distribution functions and taking moments of distribution functions. But to find current densities using distribution functions, that's not easy either, because you're not after some mean velocity. You're trying to figure out the difference between electron velocity and ion velocity, because that's what enters J. And taking moments of partial distribution functions that are not fully 3D is also a formidable task. In the lab, they fill the plasma with probes. So they can really put probes as close to each other as possible to measure current density. So when they say J, and they measure these are measuring very as accurately as they can. Well, this is what comes out of the experiment. These are experimental data, magnetic field and electron flow velocities. So what really happens in a reconnection layer is that the reconnection layer is a two-layered thing. There's an electron layer dominated by electron flows. That's a width of the order of the electron skin depth. Somebody was asking me just at coffee break, why is the density of the plasma important? The density enters the skin depth. It enters the electron skin depth, which is C over omega PE. It enters the ion skin depth, which is C over omega PI. Omega PE and omega PI are the plasma frequencies, and they have the square root of density dependence, remember? So, the electron layer, or the electron flows, are over a width of dE. The ion flows are over a larger distance. They can calculate the electric field. They find that electrons do gain energy by EY. But interestingly enough, this is surprising, but it's also true in the Earth's magnetotail. People used to think that most of the heating is really done by the field, the reconnecting electric field, perpendicular to the plane of the paper. In this experiment, as well as in other observations, it's been found that perpendicular heating, J-perp dot E-perp, is much larger than J-parallel dot E-parallel. And where this J-perp, E-perp comes from, E-perp is the whole electric field that is not the reconnecting electric field, but is actually in the plane of the reconnection, which is actually enormous energizer. Because it's associated with an electrostatic potential that you can actually calculate and measure. And these are things which have no counterpart in the Sweet-Parker theory. In Sweet-Parker, there is no Hall currents, there is no perpendicular energization. The dominant energization is perpendicular to the plane of the reconnection plane. These are happening in the reconnection plane itself, and these are all temperature profiles and J dot E profiles that are calculated from experimental data, not simulation. So why is this more dominant than the other is something that needs to be understood. There is ion acceleration, that was about the electron acceleration. There is ion acceleration and heating in the reconnection layer. And what you find is that the accelerated ions are remagnetized as they move out from the X layer and encounter larger and larger magnetic fields, and they stay in it and they get more and more magnetized, and they actually can compute exactly how much heating they're getting. And this is ion heating that comes out of this experiment as well. What they have done through thousands of shots and measurements is to quantify the various terms in this energy transport equation. And that was painful, laborious work. But they're going into data to calculate this, each one of these terms. And they've come up with a certain analysis of where from the reconnection process the energies are going. And this is what their flow chart looks like. Take this as data for which you need to develop models that have not yet been developed. The reconnection rate, identified as the magnetic energy inflow rate, is about 0.1 VA. So this is consistent with our understanding. These experiments are sufficiently small and the Lundquist number is sufficiently low that there are no plasmoids in this experiment. So we are back to the old picture without plasmoids, where you have Hall MHD improving on resistive MHD. And remember I told you we understood the onset problem? This data that onset works beautifully. No plasmoids for medium scale experiments. We understand onset perfectly, and now we are trying to quantify how energy goes. Magnetic energy outflow rate coming out of the layer is 0.49. The MHD component is about 0.22. The Hall component is about 0.27. Energy deposition rate to electrons, okay, was 20%. Change of thermal energy, 14%. Energy loss due to conduction is about 8. To ions, ions getting more energy out of the process than electrons are. The change of flow energy is this much, change of thermal energy is this much. This has been published in the Nature papers, and I believe it is the first elaborate experiment that quantifies each of the terms. The lessons that you learn from this overall is that magnetic energy is only half. Well, half of the magnetic energy coming out is going out as kinetic energy of particles. That's what this number 0.49 means. The rest of it is going to heat accelerate. And they're quantifying now, and this is a very hard problem, there is an open problem for theory. Once you know how much energy is available to go into particles, how does it apportion itself between ions and electrons? In the Earth's magnetotail, one of the cardinal observations we have is that Ti over Te is roughly 5. Why is 5 such a great number for the magnetotail? If there's a lot of reconnection going on and so on and so forth, is it still 5? Seems to be. Well, seems like ions are getting heated more than electrons, right? Well, this is not inconsistent with it. The ions are getting, but the ratio is nowhere near 5. Just to point to numerical discrepancies, the qualitative trend is there. Why is this? It's a completely unsolved problem. At the level of resistive MHD, where you don't distinguish between electrons and ions, there is much greater clarity on this issue than when you get into two-fluid models. But two-fluid models is what it is. The electrons and ions are distinguishable in the tail, in the corona, they behave differently. Only in highly collisional systems could you merge them two under one model. And this tells you about the failures of the MHD model too. MHD model doesn't distinguish electrons and ions separately. And that's why multi-fluid models is much more the future of the field. So if you look at our global MHD codes, they were based on single fluid MHD. And what are we finding? When we get into the microscopic reconnection layer and things like that, we absolutely need to understand that electrons and ions don't behave the same way. The reconnection layer has an electron layer where most of the current density is carried, and an ion layer which is broader where the electric field is. Electric field is broader than the current density itself, a notion which is completely absent in MHD or resistive MHD. The energy apportionment, a big open problem, is not even between ions and electrons. Look at these numbers. But roughly speaking, we are seeing in the inventory that reconnection leads to the liberation of magnetic energy and its channeling into flow, overall kinetic energy, and this sorts of separation between ions and electrons. So this is to just show, compared with data, and this is done mostly by cluster data. Masaki Yamada gave me very kindly. He got the Maxwell Prize this year for his work on reconnection physics, and this was his Maxwell Prize talk. He has given me these slides to show you. MRX data, if you look at energy flow, of course, everything is normalized to 1. Nobody disagrees with that. Energy outflow rate is 0.45 in MRX data. This is what it is in numerical simulations. This is what this was data from cluster. Energy deposition to ions is 0.35, 0.34 in numerical simulations. This is what cluster data is. Electron is about this. So energy deposition to ions is generally larger than to electrons. With the electrons, heat transport loss is larger than ions, implies this. Yeah, this is an attempted explanation and a speculation, but this hasn't been proven. The electrons have a loss channel that allows them to lose their energy, and that is what substantially leads eventually not to equipartition between ions and electrons, but a preferential heating of one species over the other. Let me come to the end of my story, is that magnetic reconnection, in my view, is the Sisyphus of the universe. You know the myth of Sisyphus, always trying to roll a mountain up the hill. So I was in Paris for one of my sabbaticals. It seems such a long time ago. I was having a great time. 2 years later, I don't even remember that I went on it. Life is sufficiently hectic in the US that we don't think we understand the quality of life very well. I myself am a guilty party. But anyway, in one of my forays to one of the museums, I saw this nice picture, and I thought of Sisyphus. And so Camus, who was a great novelist but not much of a philosopher, said the struggle itself is enough to fill a man's heart. One must imagine Sisyphus happy. I often think of reconnection as the Sisyphus of the universe. With that, thank you very much.